method. Yeah. Sometimes it can do better than Horner's rule, but most of the time, Horner's rule is better. Yeah. Most of the time, Horner's rule is better. Yeah. Yeah. But I also want you to compare 3 methods. Yeah. All right. But when we start, we work on monomial. Only one term, monomial. Yeah. We did some example before, monomial. Yeah. But here I want to discuss the method we used before systematically. Yeah. All right. Yeah. Given arbitrary monomial, yeah. Not a special one. Yeah, we did a special one before, but here we want to do a general monomial. Yeah. Question: how to find an efficient way to calculate this value? Yeah. All right. Yeah. 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 Here, I'll give you the reference in the textbook. Yeah. Section 6.5. Yeah. All right. Then, what do we have so far? Yeah. We learned something. Yeah. We learned Horner's rule. Yeah. Yeah. For monomial, if you apply Horner's rule, it does not improve much. Okay? If you apply Horner's rule on the special monomial, no improvement. No improvement. Okay? Yeah. Yeah. Because Horner's rule, the reason you can do much better in Horner's rule, you apply it on the general formula, yeah. Not the special monomial. Yeah. Special monomial, Horner's rule cannot improve the overall efficiency. Yeah. All right. Yeah. All right. So, yeah. But for the general case, we are very satisfied. Yeah. About the efficiency of the Horner's rule. Yeah. Right. But for special case, yeah, then you will see we're not satisfied. So if we apply Horner's rule, yeah, we won't be satisfied. Yeah. Why? Yeah. Because let me show you. Yeah. We did this x to the 4th before. Yeah. We do the square operations twice. Yeah. Yeah. 2 multiplications. Square operations twice. Yeah. The first time, first square, x times x, it's a square operation. Okay? Yeah. The second time, x squared times x squared, the second square operation. Yeah. So then we just need 2 multiplications. Yeah. All right. So here we call it repeated squaring technique. Yeah. So this technique we call the repeated squaring technique. Yeah. All right. Now, let me use the general case to show you the power of this technique. Yeah. How powerful it is. Yeah. All right. But this time we consider the exponent number n should be a power of 2. Yeah. Then we can keep doing the square operation. Yeah. Power of 2 number. Yeah. All right. So let's do experiments. Yeah. Yeah. All right. First column, k column, yeah, number. Second, monomial x to the n, but the n equals power of 2. Yeah. Yeah. The third column, we count the number of multiplications we need. Yeah. All right. When k equals 1, yeah, k equals 1, x to the 2 to the first, right? Yeah, because n equals 2 to the k, 2 to the first. Okay? So it's 2 squared, x squared. You calculate x squared, so you need 1 multiplication. Yeah. When k equals 2, you do x to the 4th. Yeah, because 2 squared. 4 equals 2 squared. So you need to do x to the 4th. So you do square operation twice. Yeah. Square operation twice. So you need 2 multiplications. When k equals 3, yeah, 2 to the third, x to the 2 to the third, x to the eighth. Yeah. So you need to do another square operation on x to the fourth. Another square operation. Yeah. So you need 3 multiplications. Okay? All right. The general case k, yeah, here, for the general case k, yeah, you need to calculate x to the 2 to the kth. Yeah. So you need to do multiplication k times. K times. Okay? Yeah. So that's the result you can enjoy from repeated squaring technique. Repeated squaring technique. Yeah. So when you calculate monomial, if you use this way, much faster than you use direct multiplication. Yeah? If you do not use this way, you do multiplication, use a for loop to do multiplication, right? Yeah. That way, much slower than this way. Yeah. All right. Let me use another example to show you the big difference. All right. Let's look at k equals 10. When k equals 10, if we use two methods, yeah. One is we run a for loop to calculate monomial. Second, repeated squaring. Okay, all right. K equals 10, then the monomial becomes x to the power of 2, 2 to the 10th. 2 to the 10th equals this 1024. Yeah. So when we calculate x to the 1024, you need 10 multiplications, right? 10 multiplications. Yeah. Yeah. Is it? Yeah. Too bright, right? Yeah. I mean, we can a little dark. Oh, not this one. This one. Yeah. This one. All right. Yeah. You can see, if you use a for loop to calculate this monomial directly, how many multiplications do you need? 1023. Not 24, 23. 1023. Yeah. But if you use repeated squaring, 10 multiplications. How big is the difference? 1023 versus 10. Big difference, right? Yeah. And this repeated squaring, yeah, is related. One of our quiz questions. Remember? Quiz questions. Yeah. Quiz question, as I remember, number 9. Okay? Quiz question number 9. If you answer quiz question number 9, study repeated squaring and this example here. Okay? Yeah. Use the understanding here to help you answer Q9 of quiz 1. Okay? Yeah. All right. Yeah. Q10, yeah. We have another topic. Yeah. Another topic. Okay. So that's why I ask you delay, but I noticed a few students already submitted quiz 1. Yeah. Yeah. So last 2 questions, you need to delay. Yeah. After this class, you can understand, answer better. Yeah. All right. Yeah. Essence of the method. Yeah. Here. Why this method can improve efficiency so much. The essence of this method, yeah, reuse the resource as much as we can to save operations. Resource, yeah, here. So our view. So how do we understand the resource here? Yeah, the intermediate calculation results. We treat the intermediate calculation results the resource. Yeah. For example, The first time after you do first multiplication, you have x squared. This x squared we treat it as a resource, okay? Because it's useful. Why we call it a resource? Because this number is useful when we calculate x to the fourth. Something useful, we treat it as a resource, okay? So it's our computing resource. It's useful when we do computation. Yeah. So this, the main idea here is when we try to improve our computation, a very important idea is try to reuse your resource, reuse your computation resource as much as you can. The more you can reuse, the better your efficiency. That's the general idea. Okay? Yeah. All right. So here, the first time we see this idea. Yeah. All right. Then next. Yeah. But in the previous slide, we consider n is power of 2, but the general case n is not a power of 2, right? Yeah. The general case n is not power of 2. Yeah. So we want to see when n is not power of 2, can we still apply the repeated squaring technique? Yeah. Yeah. All right, so here, let me use a simple example to explain. Yeah. When n is not power of 2, yeah, we use the idea, reuse the resource idea. Yeah. Try to reuse the resource. Yeah. Intermediate calculation results. That's our computation resource. Yeah. All right. Here, I select n equals 217. Yeah. Not power of 2. Okay. Yeah. But we can represent it using power of 2 numbers, sum of power of 2, right? We can represent it as the sum of power of 2 numbers. Okay? If you can do that, then we can still apply repeated squaring technique. Yeah. All right. Yeah. What is the largest power of 2 under n? Largest power of 2 under n. Okay? Yeah. The first question. Yeah. 128. Yeah. Equals 2 to the 7th. Yeah. Because if you use 2 to the 8th, that's 256. It is greater than 217. So we cannot use that. So we have to accept this 2 to the 7th. No. All right. The fastest way to get x to the 128. Yeah. So now, this time we want to do preparation. Yeah. So when we calculate, so our destination, so our goal, we want to calculate x to the 217. But to do that, we need to do some preparation. Yeah. The preparation, calculate x to the 128 for the preparation step. Yeah. How to get this number? X to the 128. Yeah. It's a power of 2. 128 is a power of 2. We can keep doing the square operations to get this number. Okay? Yeah. All right. So you can see we need to do 7 multiplications to get this number. 7 multiplications. Yeah. Because the reason is 2 to the 7. Okay? The number of multiplication you need is this exponent number, 7. Okay? Yeah. All right. Reuse the resource. Yeah. Now we use this idea. How do we reuse the resource? Okay? Yeah. Let us put all the useful intermediate results. Let's collect all the useful intermediate results in the pool. Yeah? in the pool. In our preparation, we need to, get that pool ready. Yeah. So we need this, these are the intermediate. Actually, X itself also useful. Yeah, we can put it in the pool. Yeah. All right. Yeah, so all these numbers, we may need to use some of them. Yeah, in our preparation step here. Yeah. We know these intermediate results could be useful. So we save them. Yeah, for the next round computation. Yeah. First round, preparation step. This is our first round, preparation step. Then the second round, we need to work on our goal expression. Yeah. All right. Yeah. We do decomposition. Yeah. In order to use the known numbers. Yeah. So here, all these numbers, they are known numbers. In order to use these known numbers to help us get our destination number, we need to do decomposition. Okay? Decomposition on the n number 217. Yeah. All right. The first round decomposition, we write 217 as the largest power of 2. That's 128 plus 89. Yeah. But 89, we need to split another time, 89, using power of 2, 64. Yeah, the largest possible power of 2, 64. That is less than 89. And plus some number, 25. 25, we can use 16 plus 8 plus 1. Now you can see we represent 217 as a sum of power of 2. Okay, sum of power of 2. Yeah. After we get this decomposition expression, yeah, next we can write our destination expression as product of these, our resource numbers, right? The product, okay? Yeah, the first one, x to the 128th. Yeah. Second number, x to the 64th. Yeah. Third, x to the 16th. Yeah. Next, x to the 8th, and x. Yeah. How many multiplications when you do here? 1, 2, 3, 4, right? Yeah. Yeah. After you get your resource numbers, you still need 4 more multiplications. Yeah. But to get all your resource numbers, you need 7 multiplications. Okay? In your preparation step, you need 7 multiplications. But after the preparation, you need 4 more. Okay? So the total number of multiplications you need here, 7 plus 4 equals 11. Here you can see when you apply repeated squaring operation to calculate this example, x to the 217, you need 11 multiplications. How about that? It's a big improvement, right? Yeah. Big improvement. Okay? Yeah? Yeah. So it's another interesting method. Yeah. This is our second method in our programming project number 1. Okay? 1, 2, 3. 3 methods. Yeah. So after this class, you can start working on the programming project number 1. Okay? Yeah. So because you understand everything. Yeah. All the knowledge needed. Yeah. So we covered everything. Yeah. Yeah. All right. General process. Yeah. Let's look at the general process. Yeah. Summary here. Find the largest k such that 2 to the k less than n. Yeah. Preparation. Yeah. Because you need to build that resource pool, right? Yeah. You need to, the first round, yeah, build up that resource pool. Okay. Yeah. All right. you need a k multiplications to build your resource pool. Yeah. All right. And you know, 2 to the k plus 1 is strictly greater than n. Yeah. Because in that way you can say you get the largest power of 2 less than or equal to n. Yeah. Yeah. Otherwise, you can increase that k number. Yeah. If this inequality is not true, you can increase that k number. Okay, yeah, all right. So next, based on this inequality, you can get this inequality. N less than equal to 2 to the k plus 1 minus 1. Okay, yeah. Why? It's very simple. Yeah, to understand this why, because here your inequality is strictly greater than. Yeah. You compare 2 integers. Yeah. Left-hand side, 2 to the k plus 1 is an integer. Right-hand side, n, another integer. These 2 integers, the first integer is strictly greater than second integer. Then you can say the first integer is at least 1 more than the second integer, right? Yeah, at least 1 more. Okay, yeah. So if you reduce the first integer by 1, then it should be greater or equal to second integer, right? Yeah. It has some room. Okay, so you just reduce the larger integer by 1. By 1. Okay, yeah. There is a chance it equals the first integer. Oh, yeah, good. Okay, yeah. So we near the break time. Yeah. All right. Yeah. So let me finish this slide. Yeah. So we can take a break. Yeah. All right. All right. So you n less than equal to 2 to the k plus 1 minus 1. All right. Because with this expression, you can see, yeah, any number, any n in this range can be represented as our resource numbers. Here, I want to make this argument. Yeah. All right. Yeah. Because if we use our geometric series, this is a geometric series, right? Yeah. Geometric series. When we apply our the formula, we do the summation of geometric series, we have this formula, right? Yeah. Yeah. Because if you calculate summation of this geometric series, yeah, your answer is this one. Okay? Yeah, this one. Now you see, yeah, this number is the largest in this range, right? So we want to represent the n number in this range. Yeah. So the largest number in this range, it's a sum of all our power of 2 numbers, right? In our resource pool. Yeah. The sum of all the power of 2 numbers corresponding to the terms we calculated in our resource pool. Yeah. So we can get it. Yeah. In any number in this range, we can select some of the resource numbers to make it. Yeah. So here I want to make this argument. Yeah. So that means after you prepare your resource pool, then you can represent any number in the given range. Yeah. You won't miss anyone. You can always represent any number in the range. Okay? Yeah. All right. Yeah. How to form x to the n? Yeah. So now, yeah, form. Select elements from the set, from your resource pool. Okay? Select. Yeah. 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 Select based on the decomposition. Decomposition. Okay? But this decomposition closely related to the binary representation of n, right? Here. Yeah. Yeah, because some of them could recognize recognize what we are doing here. Actually, it's a binary representation. Yeah. Corresponding to your binary representation. Yeah. Yeah. 1, 0, 1, 0, 0, you skip that power of 2. If you see 1, you need to select the corresponding power of 2. 0, you skip it. 1, 0, 1, 0. So the binary representation will tell you the decomposition information. Okay? Yeah. Pseudocode of repeated squaring. Yeah. Yeah. Very simple. Here we can use the recursion. Yeah. We can use recursion to implement this method. Yeah. So we write this repeated squaring 2 parameters, x parameter and the degree n parameter, 2. All right. First, we look at the simple base cases. Yeah. We have 2 base cases. First one, n equals 0. Yeah. X to the 0, that's 1. So our function returns value 1. Yeah. First base case. Second base case, n equals 1. Yeah. So x to the first, yeah, return x. Yeah. After that, we do recursion. Yeah. All right. Else. Yeah. Else, so we create an intermediate variable product. Store the intermediate result. This intermediate result we call the function by recursion, repeated squaring of x, second parameter n, integer division, n over 2, integer division by 2. Yeah. So it's another integer. Yeah. So we truncate the fractional part. Yeah. N over 2. Yeah. So one recursive call here. Yeah. All right. So this product temporary variable, yeah, we will use later. Yeah. All right. Then we calculate the product equals result. Yeah. Result equals product times itself, square. Square. Okay. All right. Then you will see when n is an even integer, when n is even, yeah, then no truncation, right? Yeah. If n is even, no truncation, that means this result is a good one. We can return it. Yeah. N is even. But when it is odd, there is a truncation. If there is a truncation, we need to make it up. Yeah. Because there is a 1 extra x, we need to multiply it in our final result. Yeah. So let's check it. Yeah. X mod 2, if equals 1, odd integer, then we need to multiply our result by an extra x. Yeah. Because we truncate it. Yeah. When we do this recursive call, we truncate it. Yeah. So now we add it back. Okay? Yeah. All right. If it's even, we do nothing. Yeah. Even, this, this number already a good one. Yeah. Then, at the end, we return the final result. Yeah. So it's a simple implementation, repeated squaring. Yeah. All right. Yeah. So, yeah. In our module 3, we will learn recursion. Yeah. But it's okay. In our module 1, you can apply recursion if you like. Yeah. Next topic, B.6, repeated cubing technique. This time we replace the square operation by cube operation. Yeah. Why we do that? Because it's a different method. Same idea, similar idea, but the method is slightly different. Yeah. Because we want to understand this question better. Okay? Yeah. All right. Yeah. Because when we have the background of repeated squaring, then we do this repeated cubing part by analogy. Yeah. We have experience. So we use our old, starting from this point, I did a full screen recording. Yeah, yeah, all right, yeah. Yeah, but it's okay. I can make up for the missing part. The fastest way, I just took from our previous semester video. Yeah, I mean similar, slightly different. Yeah, but I only for that missing part. Yeah. After this point, now that's our current new video. Yeah. All right. Yeah. Yeah, that part is in case you need to study. Yeah, in case you need to study, I use the from previous semester. I took that part. All right. Yeah. Now let's do analogy. Yeah. So this time, yeah, we switch power of 2 structure to power of 3 structure. Okay. All right. And we want to see, can we make some difference? Yeah. Power of 3. Yeah. Same example. Yeah. Let me show you. Yeah. Yeah. We can do the same thing. All right. This time, we still, every time we extract the largest power of 3 under n. Yeah. By analogy, yeah. So first one, 81, is the largest power of 3 less than or equal to 217. Because 3 to the 5th, that's 243. That's greater than 217. All right. So what is the fastest way to get x to the 81st? Now, this special monomial, we need 8 multiplications. Why 8? Yeah. Why 8? Yeah, let me show you the work. 8. To get the first cube, x to the 3rd, we need 2 multiplications, right? Yeah, yeah. This time, cube operation, you need a 2, not a 1. All right. The second round, cube operation, yeah, another 2 multiplications, you get x to the 9th. Yeah. The third round, another 2 multiplications, you get x to the 27th. The last round, 2 more multiplications, you get x to the 81st. But you can see after 4 rounds, you need 2 times 4 multiplications. So that's why you need 8 multiplications. All right. Yeah. So now we have our intermediate results. That's our resource. This time we need to, store them in our resource pool. Yeah. So next, our main part. Yeah. We decompose the number as a sum of powers of 3. Yeah. But look at here, the difference. We need to modify our previous, do some, small modification. The 81, we can use it twice, 2 times 81. Yeah. Yeah. Because this time our base number is 3. Base number is 3. Yeah. The coefficient 2 is less than 3. Right? Less than 3. That means you can use this x to the 81st twice, not just once. Yeah, you can use second time. Yeah, all right. So 2 times 81 plus 55. So 55, you need to do power of 3 decomposition. So you can take out 2 times 27 with 1 left. All right? That is your decomposition. Yeah. Remember, when we do the power of 2 decomposition, it corresponds to the binary representation. And when we do power of 3 decomposition, it corresponds to ternary representation, right? Yeah. Base 3, yeah. Ternary representation. ternary representation. Yeah? Yeah. See, that's an analogy part. In our ternary representation, we know the coefficient, the largest coefficient we can use is 2. Yeah? 1 less than the base number. Base number is 3. Yeah. So the largest coefficient number we can use, 2. All right? Yeah. Now we are ready to write our final expression. Yeah. This time, x to the 217 equals, this x to the 81st, we need to use it twice. Okay? In our operands, reuse. Okay? Reuse twice. Yeah. X to the 27th, also use it twice. Yeah? Reuse. Reuse the resource. Yeah. Yeah. Then, let's count the final number of multiplications. Yeah. We pay. Yeah. So this is the cost we pay. We have paid 8 multiplications in our preparation step. Then, in our main step, we need to pay 4 more multiplications. So the final answer, 8 plus 4, 12 multiplications. Yeah. Then, this time we can compare with the repeated squaring, right? This is repeated cubing. Repeated squaring, remember that number is 11, right? Yeah. Here you can see. Not better than repeated cubing. Yeah. Not better. Okay? Yeah. 12, one more. Yeah, yeah. So now the question. Is the repeated squaring the best algorithm to calculate the monomial, any given monomial? Okay? All right. Yeah. To answer this question, because we only see small number of examples, that's not enough. We need to look at a little more examples. Here, to answer that question, we cannot make our conclusion too fast. So here, we need to do another example to see if we can get some different result. So this example, I want to consider. I do not want to do a big example. So I want to consider n equals 15. Yeah, a small number, right? All right. 15, yeah. When we do binary decomposition, binary decomposition, n equals 1 plus 2 plus 4 plus 8, right? Yeah, that's 15. Yeah. Add up all the power of 2, all the consecutive powers of 2, that's 15. Yeah. But to get 2 to the 8th, we need 3 multiplications, right? Yeah. 3 multiplications. Then x to the 15, we multiply x times x squared plus times x fourth times x to the 8th. Yeah. 3 more, right? Yeah. 3 more. Yeah. 3, 3. So total 6. 6. 3 plus 3. All right? Yeah. Now let's look at cubing. Okay? Power of 3 decomposition. Yeah. All right. Yeah. Power of 3. Yeah. If you do it directly, so here I want to, although we can do the power of 3 decomposition, but sometimes we have freedom to do it slightly different. Freedom. Yeah. We have freedom. Okay? All right. So this time we want to do it slightly different. Yeah. All right. this time, x to the 15. How about we do cube operation on x to the 5th? How about that? Okay? Yeah. X to the 5th times x to the 5th times x to the 5th. Cube operation. Okay? Yeah. Two multiplication, but we need our intermediate result, x to the 5th, right? Yeah. The question, how many multiplications do we need to calculate x to the 5th? How many multiplications? The fastest way to calculate x to the 5th. X to the 5th equals x times x to the 4th, right? One more multiplication than x to the 4th. How many multiplications do we need to calculate x to the 4th? 2, right? 2. Repeated squaring. 2. Okay? Now let's do the final counting. 1 plus 2 plus 2, 5, right? Yeah. So this way, in this way, our total 1 plus 2 plus 2 equals 5. Yeah. Here you can see we do better than repeated squaring, right? 5 multiplications. If you do the repeated squaring, strictly repeated squaring, you need 6 multiplications. We can do better, right? Yeah. So you can see. Yeah. So after we see all these examples, now I want to ask you our previous question another time. Yeah. What is the fastest way to calculate any given monomial? Do you have an idea? Yeah. What is the fastest algorithm to calculate any given monomial? Okay? Yeah. So you can think about it. Yeah. So here, I do not tell you the answer. Think about it. The problem. Find the fastest. Fastest means minimum number of multiplications. Okay? Yeah, the minimum fastest algorithm for monomial. Okay? Yeah. Think about this question. Yeah. Because not that easy to answer. Not that easy to answer. Yeah, interesting. Okay? Yeah, think about it. All right. Yeah, so we complete this topic. Yeah. Although, for the analogy part, to calculate monomials using the repeated cubing. Yeah. So, yeah. Yeah. All right. Yeah. Here. Yeah. Here for the question, which one is better? Yeah. So here the question, which one is better, repeat squaring, repeat cubing? Yeah. The answer, I can give you the answer to this question. Sometimes repeat squaring is better. Sometimes repeat cubing is better. Yeah. Yeah. So the why sometimes repeated squaring better, sometimes repeat cubing is better? The answer depends on the structure of your n number. If your n number is more friendly to the power of 2 representation, then repeated squaring is better. If your n number is more friendly toward power of 3 representation, then repeated cubing is better. Okay? Yeah. But the final best way, the fastest way, the best way, you should mix both. Okay? The fastest algorithm should, sometimes you use repeated squaring. Sometimes you use repeated cubing. You mix them. You can get the optimal algorithm for monomial. Yeah. But the way, yeah, the mixing, how to mix, yeah, the way to mix those two techniques, it's non-trivial. No, it's non-trivial. No. Yeah. Yeah. It's quite challenging. Yeah. All right. Yeah. So that's this topic. Although we have the pseudocode part. Yeah. Pseudocode part by analogy. Yeah. So after you understand pseudocode of repeat squaring, we just do small modification. The base case n equals 0, n equals 1, and n equals 2, right? 2. Yeah, because for cubing we need one more base case. Okay. All right. Yeah. All right. Yeah. Then for the general case, recursive call. This we do division by 3. Yeah. After that, the result we do cube operation. Okay. The cube operation. Then next, we look at the remainder. When we do division by 3 on n, remainder equals 1. We multiply one copy of x on top of result, temporary variable. When the remainder equals 2, we multiply 2 copies, right? Yeah. Remainder equals 0, do nothing. Yeah. So at the end, we return this result. Yeah. Yeah. So that's the way. Yeah. All right. So we complete B.6. Then the last topic, B.7. Take advantage of the structure of Pascal's triangle. Yeah, here, there is a special, interesting topic called Pascal's triangle. Yeah. Here, let me show you this. Another special structure we can take advantage of when we evaluate polynomials. Yeah. All right. First, yeah, so let's look at the structure for our polynomials. First, let me give you the structure of Pascal's triangle. Yeah. All right. So the Pascal triangle, yeah. So like that. So the numbers, organized in a triangle, yeah. But these numbers follow some special rule. Yeah. Yeah. So the meaning is, because this triangle has some special meaning. Yeah. I need to give you the special meaning. All right. The meaning corresponds to binomial formula. Yeah. So in your discrete math, you have this topic, binomial formula. Yeah. Newton's formula. People also call it Newton's formula, binomial formula. What's that? Yeah. That's the formula when you calculate x plus y, parenthesis, to the nth. Yeah. Binomial formula. You need to use the combinatorial numbers. Yeah. Yeah. The combinatorial number. N choose 0. Yeah. The parenthesis, combinatorial numbers. Yeah. So there are formulas. Yeah. N choose 1. Yeah. Give you n balls, but every time you need to pick one ball from the n different balls. How many ways to choose? Choose one from n object group. Yeah. All right. Then and so on. Yeah. N choose 2. Okay. N choose 2. Yeah. How many different ways? All right. Yeah. And so on. Yeah. Yeah. So that's we call the binomial formula. All right. Yeah. And the combinatorial numbers, the definition is given n choose k definition. Yeah. We have formula n factorial over k factorial times m minus k factorial. Okay? Yeah, that's the formula. All right. Yeah. Yeah. Binomial formula. All right. Then all these numbers, the coefficients, the triangle, come to all these binomial coefficients. The top, only one corresponds to x plus y parentheses to the 0 power. That's one. Okay. The second row, it corresponds to the coefficient of x plus y to the first. Okay. So 1, 1. Next row corresponds to the coefficients of x plus y parentheses squared. 1, 2, 1, and so on. Okay? So the next row corresponds to x plus y parentheses to the third, and so on. Okay? And so on. All right. And these coefficients, there is some interesting property. For example, when you look at the 2 number here, it equals the 2 numbers, sum of the 2 numbers on its shoulder. Okay? 2 shoulders, 2 numbers. 1 plus 1, you get 2. This 3, 1 plus 2. Okay? 2 numbers on its shoulders. And 2 numbers. It is true everywhere. Okay? It is true everywhere. So this property, everywhere. All right? So that's we call it Pascal's triangle. All right. So then, with this special structure, we can take advantage of the special structure to use the minimum number of multiplications with, because there is a special pattern we can take advantage of. All right. So we can do much better than Horner's rule. Because if you do not take advantage of the special pattern, you apply Horner's rule, that's not the fastest. All right. Here, let me show you one simple example. How many multiplications do we need to calculate this special polynomial? It's not a general one, it's a special one. 1 plus 5x plus 10x squared plus 10x cubed plus 5 times x to the 4th plus x to the 5th. All right? So if you do not take advantage of the special structure, how many multiplications do you need? Think about it. By Horner's rule, how many multiplications do you need? By Horner's rule. So let me ask you this question. Okay? By Horner's rule, for this one, 4 multiplications. Not 5, okay? Although degree is 5, but if you look at Horner's rule, the last multiplication, we do not need to do it. Because the leading coefficient is 1. The last multiplication is an times x, right? An is 1. So here, the reason we need a 4, not a 5, look at last term. Last term, in Horner's rule, the last multiplication is an times x. But our an is 1. Why you need to do 1 multiply x? Right? You do not need to do 1 multiply x. So you can save 1 multiplication by Horner's rule. By Horner's rule, 4 multiplications. All right. Now, we want to do better than Horner's rule. All right. this structure, look at this structure. This structure corresponds to one of the rows in this Pascal's triangle, right? The coefficients. Yeah, exactly this row in the Pascal's triangle, right? That means by the binomial formula, this polynomial should be this polynomial, right? Yeah. Although y equals 1, so here, yeah, this one, x plus 1, okay? Y is 1, yeah, right, yeah. So you see, so we discussed, all right. So then, by Pascal's triangle, it is x plus 1 parenthesis to the 5th. Yeah. Because we only count number of multiplications. We do not count addition, right? Yeah. We do not count addition, so then some number to the 5th, we need 3 multiplications, right? Yeah. So we did the first multiplication, second multiplication, the third, yeah, the third, yeah, one more, yeah, 3 multiplications, okay, yeah. So in this way, we can reduce the multiplication number by 1, right? Yeah, yeah, yeah. So you can see, when we take advantage of the special structure, we can do better than Horner's rule. Yeah, we can do better. Yeah. Yeah. Right? Yeah. 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 Then, remember one of the quiz questions on this one. One of the quiz questions. Now, after we finish part B, yeah, you can answer that question better. Yeah. Yeah. Some students answered before we complete part B. Yeah. Then there is some chance you may miss that question. There is a chance, all right? Yeah. Yeah, because I saw some students already submitted. Yeah. So there is a chance. Yeah. Yeah. All right. Yeah. So now we complete the whole chapter. Well, not chapter, part B. Yeah, part B. Next, we need to start part C. Yeah. All right. Yeah. So let's start. Oh, yeah. Yeah. On this side. Yeah. Because I have my 2 computers. I have recording side and the presentation side. Yeah. Yeah. All right. So I only need to change at the presentation side. Yeah. Recording side, I never need to touch the recording side. Yeah. All right. Yeah. So then we switch to the part C. All right. Part C, it's a small topic. Yeah. 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 So we can, after we finish part C, so we can start part D. Yeah. Today, I think. Yeah. Hold it. Oh, what's wrong? All right? Yeah. Yeah. Topic, role of data structures in algorithms. C.1, search unordered arrays. Yeah. All right. So let's look at our question first, search an unordered array. Yeah. It's a simple computing problem, yeah, but very basic, so we need to learn. Given an unordered array, yeah, and a search key K, so we need to find an index I such that A of I equals the given key K. Yeah. So that's the search type problem. Yeah. All right. And the reference. Yeah. Data structure array. So here I'll give you a reference, section 2.1. Yeah. Yeah. For this class, we will study 3 basic types of algorithms. Yeah. The 3 basic type. Yeah. All right. Yeah. First one, search. Second one, sort. Yeah. Third one, selection. 3 basic type. Yeah. Selection. Okay. Yeah. What's the selection type problem? Finding the first smallest element, finding the kth smallest element, yeah, for a given k. Yeah. So those problems we call a selection problem. Yeah. All right. Yeah. So this class we will spend a lot of time on these 3 basic types of algorithms. Yeah. All right. This one is our first search problem. Yeah. All right. Why the data structure are important in algorithm design? Yeah. At this point, yeah, after we learn, several classes, yeah, so we should have some idea. Through data structures, we can make our data well organized. We know it's important to organize our data in a special way. Yeah. Then we can take advantage of the special properties of our data. That is important. Okay? All right. So find the required data fast. When you organize your data in a special structure, then you can find the data much faster. You can save a lot of time. Yeah. When you search, for some special data items. Yeah. All right. So then you can get a better overall performance. So that's the reason. So we need to choose appropriate data structures. All right. For this example, we just choose the simplest data structure array. Simplest. Yeah. Yeah. All right. The basic operation, comparison. Here, yeah. In order to solve the problem, we need to do comparisons. Yeah. So that's our basic operation. Yeah. All right. Compare K and A of I. When we do this comparison, so initially I equals 0. We compare the first element with K. Yeah. And when we do the comparison, we have 2 possible outcomes. Yeah. 2 possible outcomes. One, K equals A of I. Then we find the element we need, so we can stop. Because you'll find it. And the other outcome, K is different from A of I. Yeah. So in this second case, K is different. You need to keep doing the comparisons. Yeah. So you need you need to more iterations. Right? Yeah. So next iteration, you compare K and A of I plus 1. Yeah. Then 2 possible outcomes. Yeah. Right? Yeah. But you keep doing all the iterations at the end, yeah, because at the end, you may not get any match, right? Yeah. Because at the end, there is a possibility there is no match. If there is no match, your function should return -1. Yeah. So it's not a valid index. Yeah. The valid index should be non-negative number, right? Yeah. So here you use a invalid index number to tell users no match. The special meaning, no match. Yeah. All right. So that's the whole algorithm. Yeah. 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 All right. So here first I describe the whole basic search algorithm. Yeah. Yeah. So this algorithm, people call it, two commonly used names. The first one people call sequential search. The second one, people call it linear search. Yeah. All right. Yeah. Yeah. So for this algorithm part, the details of the implementations, so we do not need to do any discussion. But our main focus here, we want to do the analysis. We want to do analysis on its efficiencies. So through this example, we want to learn some basic concepts. All right. Yeah. To do here, count the number of comparisons. We need to count number of comparisons. Yeah. But there are many cases. Okay, all right. Yeah. Yeah. So here, when we do this chart here, we want to list all the possible cases, including the last one, no match case. All right. The number of comparisons for all these cases, we can see easily. The first case, one comparison. When k equals the first element, one comparison, equals second element, two comparisons, and so on. When k equals the last element, n comparisons. Yeah. All right. Then no match case. Yeah. Other than k equals the last element, there is a no match case. Also n comparisons. So that's all the possible cases we need to consider. Okay? Yeah. Then we need to make conclusion. Yeah. So that's the all the possible outcomes we may have. Yeah. But we need to do the discussion here. Do some discussion. Yeah. First concept, best case efficiency. Yeah. That concept. What is the best case efficiency? One comparison is the best case efficiency. Okay? All right. Then, second concept, worst case efficiency. Yeah. Worst case efficiency. The last two cases and n comparisons. That's the worst case efficiency. Yeah? Yeah. So very easy, these two cases. Yeah. But then there is another important concept we need to learn. Yeah. Actually, that's the main topic we want to learn in this part. That is the overall efficiency. So we need to look at the concept. How to measure the overall efficiency for this search algorithm. Okay? Yeah. So we need a lot of discussion on this overall efficiency. Yeah. So let us take a 10-minute break. After you come back, second half, so we will complete discussion of this overall efficiency.